So in this video I want to talk about numbers that have fractions. So the number that we can represent using binary representations, we have seen several of them so far. You have seen positive numbers, in which another name is unsigned binary numbers, in which we said that if we have n bits, each one of these bits has a weight associated with them. So 2 to the 0, 2 to the 1, all the way to 2 to the n minus 1 if it was like an n bit binary number. Then we had negative numbers, in which we had the 2's complement representation, in which for n bits again we had some weight associated with them. So 2 to the 0, 2 to the 1, 2 to the n minus 2, and the last or the most significant bit had 2 to the n minus 1 with a negative sign. And also we saw the sign magnitude numbers, in which the most significant bit is the sign bit, which had a weight of -1. So this one is 2 to the 0, 2 to the 1, 2 to the n minus 2, and finally this one had a weight of -1. But in all of these cases the numbers were whole numbers, so we didn't have any fractions. In this video I want to talk about different ways that we can represent fractions using binary numbers. So there are two common notations for representing numbers with fractions using binary values. The first one is a fixed point binary number, and the second type is a floating point binary number. In fixed point binary number, the number of integers and the number of fractions is determined beforehand, so they won't change. On the other hand, the floating point numbers, the binary point or the fraction point floats to the right of the most significant one that we have in our binary representation. So let's just go through them one by one and see how they work. So for the fixed point binary numbers, it's a good thing that we start with an example. So let's just say we want to represent 6.75 using 4 integer bits and 4 fraction bits. So this is the representation using 4 integer bits and 4 fraction bits. So these 4 bits are used to represent the integer part, and these 4 bits are used to represent the fractions. So for the integer part, you know how the weights are calculated. So this is 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. For now, let's just only focus on unsigned numbers with fractions. As you can see from the most significant bit, we basically reduce the power of the weight one by one. So if we continue this, the first fraction bit has a weight of 2 to the -1, the second one has a weight of 2 to the -2, 2 to the -3, and 2 to the -4. This is because we have predetermined that this specific number should have 4 integer bits and 4 fraction bits, right? So in another word, this binary point or this fraction point is implied. You don't represent it, but when you see that it says 4 integer bits and 4 fraction bits, you basically divide this 8-bit number into these two sections. And as you can see, you can use these weights to come up with a number in decimal format. As you can see here, this one has a weight of 2 to the power 2. This one has a weight of 2 to the power 1. This one has a weight of 2 to the power -1, or it's 1/2, or 0.5, and this one has a weight of 2 to the negative 2, or 1 over 2 to the 4, 1 over 2 to the 2, or 1 over 4, or 0.25. So again, the binary point is implied, it is not explicitly mentioned, and the number of integers and the number of fraction bits must be agreed upon beforehand. So let's just say if I give you the same 8-bit, but I just say this is 5 integer and 3 fractions. In that case, the integer number is going to be, the integer part is going to be 0, 1, 1, 0, 1, and the fraction is going to be 1, 0, 0. So this is equivalent to this is 8, this is 4, and this is 1. So this is 13, and this one is 0.5. So 0.5. So based on this condition, this is 13.5, and it's not 6.75, right? So this is very important, that you need to pay attention to the number of integer bits and fraction bits in fixed point numbers. So let's just go for another example. We want to represent 7.5 in base 10 using 4 integer bits and 4 fraction bits. So we have 4 integer bits, an implied fraction point, and 4 fraction bits. So if you remember from before, 7 is 0, 1, 1, 1, and 0.5 is going to be 1, 0, 0, 0. So the representation is going to be 0, 1, 1, 1, 1, 0, 0, 0. So this is 7.5, 10 as a 4 integer bit, 4 fraction bit, fixed point binary number. So what about if we want to represent a signed fixed point number? The procedure is exactly similar to what we had before. So whether we want to use sign magnitude or the 2's complement, the procedure is exactly the same. So let's just go over one example. In the previous slide, we had 7.5 represented as a 4-bit integer, 4-bit fraction, fixed point binary number. So it was 0, 1, 1, 1, 1, 0, 0, 0. So now let's just show the sign magnitude representation of this number using 4 integers and 4 fractions. If you remember from before, for sign magnitude numbers, the most significant bit was being used to represent the sign. So the most significant bit is here. So since we want to make this number a negative number, we can show it as 1, 1, 1, 1, 1, 0, 0, 0. So this is basically the sign bit. What about for 2's complement? As I said, the procedure is exactly the same. So 0, 1, 1, 1, 1, 0, 0, 0. We have to first flip all the bits. So basically whenever we have 0, we replace it with 1. Whenever we have 1, we replace it with 0. And then for the next step, we add 1. So if I do this, we have 1 plus 1, it's 0, 1. So we have 1 carry over here, 1 plus 1, it's 0, 1. We have 1 carry over here, 1 plus 1 is 0, and then 1 carry, and then this is going to be 1, and then 0, 0, 0, and 1. So this is 2's complement of basically 7.5, which is going to be negative 7.5. The same problems that we had for the integer sign magnitude numbers, we still have it here too. So it is usually more preferred to use 2's complement to represent negative numbers, but nonetheless the procedure is exactly the same, because the fraction point is only implied. We don't explicitly represent that. So that was how we defined fixed point binary numbers. For the floating point binary numbers, the binary point or the fraction point floats to the right of the most significant one that we have in our number. So this is very similar to the decimal scientific notation that we have seen before. So for example, if we have value 273 in base 10, and if you want to write it in scientific notation, we use a fraction point, and we put this fraction point to the right of the most significant digit. So we have 273, we put the fraction point to the right of the most significant digit, which is 2 here, and then we multiply this by a power of 10. So let's say if I have 538, this is equivalent to 5.38 multiplied by 10 to the power 2. If I have 6792, this is going to be 6.792 multiplied by 10 to the power 3, right? So generally speaking, the number will be written in a scientific notation as below. So we have either the positive or negative depending on the number. Then we have m, which is called the mantissa of the number. We have b, which is the base, and we have e, which is the exponent. So for example, for the for 2253, so if I let me just write it like this. So for 273, the mantissa will be 2.73, the base is going to be 10, and the exponent is going to be 2. For 6792 that we saw before, it's going to be 6.792, that's the mantissa, the base is 10, and the exponent is 3. The floating point binary numbers are exactly the same. The only difference is the base, right? For decimal number, the base is 10. For binary numbers, the base is going to be 2. So let's just see how we can represent floating point binary numbers. So since we have several components, it is good that we divide the number of bits that we want to use to represent the floating point binary number into several sections. So assuming that we are using 32 bits, the most significant bit is representing the sign. We use 8 bits to represent the exponent, and we use 23 bits to represent the mantissa. Of course, we don't have to use any bits to represent the base, because since it's binary number, we know the base is always 2. So let's just take a look at one example. Here we want to represent the value 228 in base 10 using a 32-bit floating point representation. What I will do here is that I will show 3 different versions of this representation. The final version is an IEEE standard. It's called IEEE 754 floating point standard, right? Which is very common in all the computer systems. But we will go step by step so you see how this final standard is being derived. So let's just go through it step by step. For the first representation, first we have to convert the decimal number to a binary. And one thing that you should pay attention is that these steps should not be reversed. So the first step is to convert the decimal number to the binary number equivalent. So for doing this, we use the continuous division as we did before. So if we do that, 228 in base 10 is going to be equal to 111,001,00 in base 2 or in binary. So now that we have this, we write the number in binary scientific notation. So the keyword here is binary. When you have binary, that means that the base is going to be 2, right? So what we basically are doing is that we use this fraction point, we place it to the right of the most significant bit. So in this 8-bit number, the most significant bit is 1. So we put the fraction point here, and then we can represent this number as a binary scientific notation as 1.11001 in base 2 multiplied by 2 to the power 7. And if you do the calculation, you see that these two are exactly equal. So now that we have derived this, we see that the exponent here is 7 and the mantissa is 1.11001. So now that we have this, we have to fill out the 32-bit element that we had. So the sign bit is positive because the value that we have is a positive number, positive 227. So the sign bit is going to be 0. The exponent part, we said that it is 8 bits. So the value for the exponent is 7. So 111 is representing 7. And since we want to make it 8 bits, and since it's a positive number, we just 0 extend 111 and make it at 8 bits, right? So the exponent part is going to be 00000111. As for the mantissa, we neglect the fraction point. So this is, you can say, very similar to the fixed point representation in a way that in fixed point representation we basically implied the fraction point, right? So this is very similar to that. Another similarity is that you can think of mantissa as a fixed point floating number, binary number, in which only one bit is used to represent the integer part and the rest is used to show the fraction part, right? So if we do that, we basically put the values that we have here. So 1, 1, 1.1, 1001, basically the mantissa that we had on top, and we just represent it like this. We neglect the floating point and we represent the mantissa like this. So since the mantissa has 6 bits only, the rest of the bits is going to be 0. So this is the first representation that we have for a floating point binary number. One thing that you should notice is that the first bit of the mantissa is always 1. Why do you think we have this? The reason is that we purposefully put the floating point to the right of the most significant bit that we had, right? So since we are working with ones and zeros, right? Let's say if I have 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 1. So all these zeros that are to the left, they don't contribute to the value of this number, right? So they can easily be eliminated. When you want to put the floating point and show it as a binary scientific representation, you always put the fraction point to the right of the most significant one that you have, right? And then you put 2 to the power, for example, here we have 6, right? So because of that, this in this binary scientific notation, this bit is always 1. So since it is always 1, we don't need to store it. Basically, we just imply it, right? This is called the implicit leading one. The same way that we imply the location of the floating point, we do the same for the value of this first bit. The rest is practically the same as the first representation. We have the sign bit. Since it's a positive value, positive 228, we just put 0. For the exponent was 7. 7 is represented by 111. Since it's only 3 bits, we 0 extend it. We add 5 zeros to its left. And then finally, for the mantissa was 1.11001. We neglect this and we put this part in the fraction part or the mantissa of the 32-bit number that we have. And the rest of the values, whatever comes after this, is going to be 0, right? So this is the second representation that we have. As you can see, using this, we basically free up 1 bit in mantissa. That gives us some flexibility on the range and values of the numbers that we can store in a 32-bit variable like this. But still there is something you can say missing. What is that? Here what we have is the value of the power. It is positive. So what if we have a negative value for this power? What if we have a value that looks something like this? And then if we want to write it in the binary scientific notation, we have to write it like 1, 0, 1, 1, 0, 1, and then 2 to the negative 3. So in this case, these two representations don't allow us to do that. That's why we have this modified version which uses a biased exponent, in which we basically add a fixed value or a bias to the exponent component. So in a 32-bit representation that we use here, in which the exponent has 8 bits. So if you remember from before, using 8 bits, we can represent any value between 0 and 255, right? Since we want to be able to represent negative numbers too, one way is to either consider this as a sign magnitude or a 2's complement, right? But this is usually not practiced because these complicate things. So instead what we usually do is that we add this additional bias to account for both positive and negative values of the exponent component. And when we want to recover or read the data from memory, we know that we have to subtract this 127 from the exponent component. So now that we have this, the final result, is going to be 0, 1, 0, 0, 0, 0, 1, 1, 0, and then the rest is going to be 1, 1, 0, 0, 1, 0, 0, and then 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and then 0, 0, 0, 0. So this 32-bit number is representing 228. And of course, since it's a very long number, you can use the hexadecimal representation as well. If you remember from before, we divide this starting from the rightmost bit into sections of 4 bits, and for each one of them we use the hexadecimal representation as we have seen before. So when we do this, the hexadecimal representation of 228 is going to be 0x43640000. Let's just take a look at another example here. What we have is a negative number now. So we want to represent negative 58.25. So what we do is that we start with the positive number. We have 58 as the integer part that can be represented by 111010, and we have 0.25 as the fraction part, which can be represented as 0.01. Remember, this one had a weight of 2 to the negative 1, this one had a weight of 2 to the negative 2, which is 1 over 4, which is 0.25. So now that we have this, the next step would be to write this number in the binary scientific notation. We take the floating point or the fraction point, we put it to the right of the most significant bit, and then based on that we come up with the mantissa, and we come up with the exponent. So now that we have the mantissa and we have the exponent, also since this is a negative number, first we put the sign bit as 1, representing that this is a negative number. For the exponent part, the exponent was 5. We add the bias, which was 127 to 5, which make it 132. So this is the representation of 132 in binary. And finally, for the 23 fraction bits, we eliminate the leftmost one, because we know that it is definitely 1, and we represent the rest into mantissa component of the number that we have. And again, this is a 32-bit. If we divide it into sections of 4, starting from the rightmost bit, so this is 4, and then this one is 4, and then this one is the last set of 4 bits. And if we represent each one of them using their hexadecimal equivalent, this is going to be the hexadecimal equivalent of negative 58.25. There are some special cases when we are representing numbers in this format. For number 0, the sign is represented with x, and the exponent and fraction parts are all zeros. For positive infinity, the sign is 0, the exponents values are all 1s, and the fraction is 0. For the negative infinity, the sign is 1, the exponent part is all 1s, and the fraction is 0, all zeros. And for nan, or not a number, the sign component is x, the exponent is all ones, and the fraction can be any non-zero value. Of course, these are more advanced cases. If you're interested, you can refer to the book or any related resources to find out more about them. There are different types of floating point numbers. We can have single precision floating point numbers in which we use 32 bits to represent the number. The examples that we saw before are examples of single precision floating point numbers, in which we have 1 sign bit, 8 exponent bits, and 23 fraction bits, and the bias is 127. We also have double precision floating point numbers, in which we use 64 bits to represent the number. Again, we have 1 sign bit, but here the exponent component has 11 bits and the fraction component has 52 bits. As for the bias, we use a value of 1023 as the bias for this representation. So in this video we have learned how we can deal with numbers that have fractions. We talked about different ways of representing numbers using fixed point binary numbers, and also we talked about different representations of floating point binary numbers.